Guys, welcome back to my YouTube channel. We are still on the course STA 221 Design and Analysis of Experiments, and the aspects that we are still considering under this course is the Completely Randomized Designs, the CRD. And in our last video, we were able to derive the equation of the overall mean, which is mu. We estimated the first parameter of the CRD model. The CRD model is given as Yij equals to mu plus tau I plus Eij, where Yij stands for each observation. We say jth observation under the ith treatment, each observation under each treatment. So there could be more than one or two treatments. So we have different observations under different treatments. So that's what Yij stands for. Mu stands for the overall mean, the grand mean of all the observations under all the treatments altogether. And tau I stands for the ith treatment effect. And the Eij stands for the random error. So today we are going to be looking into estimation of the CRD parameter tau I. Same method we applied in our last video when we were deriving the equation for mu is the same method we are going to be applying today, and that method is the least square estimate method. What we basically do in the least square estimate method is that we make Eij, which is the random error, the subject of this equation, and after making it the subject of the equation, then we square it and we sum it, which gives us what we call sum of squared error, the SSE. So it is the sum of squared error that we now differentiate with respect to the parameter that we are trying to estimate in this model. So let's go through that. This is Eij, which is the random error. We make it the subject of the equation. So we have Eij equals to Yij minus mu minus tau I. So the next step is to square the error term. So we square the entire equation. We have Eij squared is going to give us Yij minus mu minus tau I all squared. So we sum it. Since the parameter that we are concerned with is tau I, so we sum over j. We do not sum over I because based on the assumptions of the CRD model, the summation of tau I over I is going to give us 0. If we sum all the treatment effect, the sum of all the treatment effects is 0. So we sum over j. So what we then have is going to be summation Eij squared j from 1 to n is equals to summation Yij minus mu minus tau I all squared j equals 1 to n. Remember, our summation Eij squared is the sum of squared error, which we can abbreviate as SSE. SSE stands for sum of squared error. So our sum of squared error is what is equals to j equals 1 to n of Yij minus mu minus tau I all squared. So based on the least square estimate method, like I said earlier, we have to differentiate SSE, which is the sum of squared error, with respect to the parameter that we are trying to estimate. So the parameter we are trying to estimate is tau I. So tau I becomes our variable, and by the principle of partial differential calculus, if we differentiate this, the SSE, the tau I, is going to give us minus 2 summation j equals 1 to n of Yij minus mu minus tau I. And from there, we minimize it. And as minima, the y dx is always equals to 0. So therefore, our DSSE, the tau I, is going to be equals to 0. This implies that from this equation, we are going to set this entire expression on the right hand side to 0. So therefore, minus 2 summation j equals 1 to n Yij minus mu minus tau I is equals to 0. In order to have a clean equation, we divide all through by minus 2. So we have divided by minus 2 divided by minus 2. Minus 2 cancel minus 2 here. We are left with summation j equals 1 to n Yij minus mu minus tau I equals to 0. So from here, we then open the brackets. So by opening this bracket with this summation, we are going to get summation j from 1 to n of yij minus n mu. The reason why the summation transforms to become n is that n is the number of jth observations, and since mu is constant to this summation, so the summation becomes n. So, and the same for tau I. This treatment effect is over I, not over j. So it's going to be constant to tau I too. That is why it becomes n tau I. So from here we make the tau I the subject of the formula. So we are having summation yij j equals 1 to n minus n mu equals to, if we move this to this side, it becomes plus. So we have n tau I. So divide all through by n. So when we divide through by n, we have summation yij j equals 1 to n minus n mu equals to n tau I divided by n divided by n divided by n, and from this n cancels n. So we are left with summation yij j equals 1 to n all over n minus mu cap equals tau I cap. So from this equation, finally we've been able to derive an equation for our tau I. So tau I cap, which is the estimated parameter tau I, is equals to summation yij j equals 1 to n all over n minus mu. And recall that the estimated mu is summation yij I equals 1 to k and j equals 1 to n all over kn. So if we apply it to the equation, to this equation above, we have our tau I to be summation j equals 1 to n of yij all over n minus summation yij I equals 1 to k, j equals 1 to n all over kn. And from there, in order to write this in a short form, we are going to have this as tau I equals yi dot, and the reason why it is yi dot, this dot represent a sum. The reason why it is yi dot is because the summation is only over j. So this j subscript has been summed. The observations j have been summed. So that is why we have yi dot. So over n minus, and for this we already know from our last tutorial that it is y dot dot, because there are two summations. So over kn, which gives tau I equals to yi dot bar minus y dot dot bar. Finally, this is the equation of the parameter tau I, and it is also known as the deviation of each treatment's mean effect from the overall mean effect. Thank you.